Let's start chapter number 5, Forces and Matter. We are going to discuss about the law of Hooke and the forces that influence the tense spring. You see here in this table, we have zero load. The length of an string is 20 centimeter and there is no extension because there is no load. But when we increase the load, the length increased from 20 to 20.6, which shows an extension of 0.6. Similarly, when the load further increases to 2, the length further increases from 20.6 to 21.2, hence the extension is now 1.2. As more and more load you keep on increasing, you see that the extensions also kept on increasing. This extension is equals to length of elongated spring minus the original length. So extension is that whatever is your elongated spring length 21.8 minus the older one 21.2, and you will get how much is the extension. This is a Robert Hooke law, who was born in 1635, and he formulated this equation that how with the increase of load the length of an object can be increased. So Hooke found that the degree of which the spring extends is directly related to the force applied to it. In other words, if you increase the weight to twice its original amount, the extension will also increase to twice its original length. This is called as Hooke's law, and it is applicable on springs. So for any spring, calculating the load, the force divided by the extension result in the value known as spring constant K. So Hooke's law has a constant called as spring constant, and how you can find the spring constant? You can divide the force, the load with the extension, and you will get a constant as long as the spring has not been stretched beyond its elastic limit. So there is a limit on it, which is that the spring should be within its elastic limit. If it goes beyond its elastic limit, then it will not turn back into its original shape. So spring constant load is equals to spring constant times extension. Load is the force, so force is equals to K times X. X is an extension, K is a constant, F is the force. Up to point X, the extension is directly proportional to the applied load. Point X represents the limit of proportionality. So past point X, the spring still operates elastically and will revert to its original length once the force is lifted. Upon reaching the elastic limit, the spring starts to behave in a plastic manner and fails to return to its initial length. It becomes permanently elongated then. So, pressure, what would be more painful? The more weight will be having the more pressure. So, getting stepped on by a 55 kg woman or being stepped by a 3-ton elephant. So, of course, more force will be having more weight. So, here we need to calculate the pressure, which is equals to force over area. Force is quantified in newtons, area is quantified in square meters, and pressure is expressed in newtons per square meter. The alternative for Newton per square meter is Pascal. So if you say Pascal, it means you are saying Newton per square meter. So let's talk about our numerical here. A box on the floor has a weight of 250 Newton. The area that the box rests on is 0.25 meters square, and we need to calculate the pressure under the box. So pressure formula is equals to force over area. We divide it when we get the answer 1000 Pascal, or you can say Newton over meter square. Same thing. Second numerical, a hose causes a force of 8000 Newton from the water over an area of 0.5 meter by 0.5 meter. Calculate the pressure. So we need to calculate F over A. F is given, area is given, and we will find the pressure. Here 0.5 times 0.5 will give you 0.25 meters in area. Some examples of pressure: raise the pressure by minimizing the area. The surface area at the edge of a knife blade is quite minimal. Below it, the pressure is significantly high, allowing the blade to penetrate material like fruit with ease. The studs on the saucer cleat have a limited surface area in contact with the ground. As a result, the pressure under the studs is enough for them to embed into the ground and enhance traction. So, here is an example of soccer, here is an example of knife, explaining you how the pressure works. Then we have an example of air pressure. Atmospheric pressure exerts force in every direction. As you ascend through the atmosphere, air pressure will decrease. The density of the atmosphere is greater at lower altitudes. At sea levels, the atmospheric pressure is approximately 1000 kilopascals. How the pressure is relevant to Hooke's law. Again, first, what is Hooke's law? It is extension directly proportional to force applied. As long as the elastic limit is not exceeded, mathematically we can write F equals to Kx. F is the force, x is an extension, k is the spring constant. More force means more deformation. What is air pressure? Air pressure is caused by air particles colliding with surfaces. So, more air particles, greater force, less air particles, smaller force. Pressure is force per unit area, P equals to F over A. What the atmosphere diagram is showing us, as you go higher in the atmosphere, air density will decrease. Number of particle collision will also decrease, hence the air pressure decrease. At sea levels, air is dense, pressure is high. At high altitude, air is thin, pressure is low. How Hooke's law connection here is important. Imagine replacing a spring with a balloon or a sealed syringe, lungs, or flexible membrane. These objects deform due to air pressure. The air pressure provides the force. The object stretches or compresses. The deformation follows the same idea as Hooke's law. More pressure means more force, means more deformation. Less pressure means less deformation. Simple exam style example: at sea level there will be high air pressure, balloon is compressed more, greater deformation. At high altitude, lower air pressure, balloon expand, less external force. This is the force causing extension, compression, exactly what Hooke's law describes. So also for the exam perspective, change in air pressure change the force acting on object, and this can be tested as this force causes elastic deformation, and it can be tested using Hooke's law. With this, we have finished our chapter. See you in our next chapter.